So in this final video cast, chapter 17, the marathon chapter of video casts, we're going to take a look at what it takes to make various solutions of ions precipitate and calculate how much of something it would take to form various precipitates. Please make sure you have your example problems like these out in front of you to follow along with and take notes. This problem says a solution contains 1 times 10 to the negative second moles of silver ion and 2 times 10 to the negative second molarity of lead ion. When chloride ion is added to the solution, both silver chloride and lead chloride precipitate from the solution. What concentration of chloride ion is necessary to begin precipitation? Which salt will precipitate first? And then it gives us the KSP for both silver chloride and lead chloride. So what they're saying in this problem is we've got this beaker, and inside of there we've got a water or an aqueous solution of silver ion and lead ion. Silver ion happens to be of the concentration of 1 times 10 to the negative 2, and lead ion happens to be in the concentration of 2 times 10 to the negative 2. And it said we're going to dump into this beaker some source of chloride ion. It could be hydrochloric acid, it could be sodium chloride, something where the cation is not going to affect the solubility and pretty much do nothing in solution. So when we add these, we're going to form two different compounds. One of them is silver chloride with a KSP of 1 times 10 to the negative 10th, and the other one is lead chloride, PbCl2, which has a KSP of 1.7 times 10 to the negative 5th. And it's asking us which one of these two salts will form precipitate or a solid first. Well, we can use the KSP expression for each one of these to solve for the chloride ion for each one, and then we can see which one's smaller. And the one that's the smallest, of course, will precipitate first because you need to add the smallest amount of chloride ion before you can make it precipitate. So, moving these, let's first write what the equation would be for our silver chloride. And if we write the KSP expression for this, it would be silver ion to the first power times chloride ion to the first power. And this is equal to 1.8 times 10 to the negative 10th. And we're told in the question that the silver ion concentration is 1 times 10 to the negative 2. And so we can put that in for the silver ion concentration. And then this, of course, is equal to 1.8 times 10 to the negative 10th. And if we solve this, we'll divide both sides by 1 times 10 to the negative 2. These cancel, and our chloride ion concentration needed for the precipitation of silver chloride now would turn out to be 1.8 times 10 to the negative 8th. 1.8 times 10 to the negative 8th. That's how much chloride ion it'd have to add just to get it to start to precipitate AgCl. Now, PbCl2, I could do the same thing with, and I'll get some lead ion, some chloride ion. I can write the KSP for this critter, or Pb plus 2 times Cl minus, but don't forget to square it here because there's 2 Cl minuses from the PbCl. And I'm told up here once again that the lead ion in this solution is 2 times 10 to the negative second, and the KSP here for lead chloride is 1.7 times 10 to the negative 5th. And once again, I'm going to solve for the chloride ion concentration just like I did up here with the silver. So divide both sides by 2 times 10 to the negative 2. It's going to cancel over here. And then don't forget this is squared, so I'll have to take the square root of both sides. And then once I solve that using my calculator, it turns out that the chloride ion concentration here is 2.9 times 10 to the negative 2. So if you take a look at these two, here's the chloride ion concentration necessary to precipitate the silver chloride, and then here's the chloride ion concentration necessary to make the lead chloride. Well, if you look at that, this one is way, way smaller than this one. And so silver chloride will precipitate first, and then after I add a bunch more, times 10 to about the 6th more, then I'll start to precipitate my lead chloride. And as a matter of fact, if you had this bucket full of silver chloride and lead chloride, you could separate the two out. You could first add just a small amount and separate out all the AgCl, and then once you've filtered that off, then you could go ahead and you could start to add more of it, and you could precipitate all the lead. That's one possible way, using different solubilities to separate two salts like this. Let's look at the next problem. The next problem says a solution consists of 0.05 molar magnesium ions and 0.02 molar copper ions. Which ion will precipitate first as hydroxide is added to the solution, and what concentration of hydroxide is necessary to begin the precipitation of each cation? And just like the last problem, they give us the KSPs for each of the salts that's going to form. During this one, make sure you have your calculator available, because I'll have you stop along the way and you can see if you can do the solving just like we did in the last problem. So, just like we had last time, we've got a beaker, and inside of this beaker is a solution that's got magnesium ions and copper ions, and the two ions are present in different concentrations. Magnesium's concentration is right here, and copper's is 0.02. We can write the KSP expression for both of these salts, and maybe you can just do it right from taking a look at the formula. Magnesium hydroxide right here. This is for the magnesium one, and then this is going to be the KSP for the copper one. Pause the video now and see if you can write the KSPs for the magnesium salt that'll form and for the copper salt that'll form. Hopefully you got the magnesium to the first power and the hydroxide to the second, the copper to the first and the hydroxide to the second, because when these break apart, of course, you will get one copper ion and two hydroxide ions, and so you need to raise the hydroxide to the second power. Once you've got these written, now you can put in the concentrations for magnesium and the concentration here for copper and set them equal to their KSPs. And it tells us that magnesium hydroxide's KSP is 1.8 times 10 to the negative 11th, and it tells us that copper hydroxide is 2.2 times 10 to the negative 20th. Pause the video now and see if you can solve for the hydroxide concentration for magnesium and the hydroxide concentration for the copper hydroxide that would form. Hopefully set the magnesium one up like this, where you put 0.05 in for magnesium, the hydroxide was squared, and that equals 1.8 times 10 to the negative 11th, divided both sides by 0.05, and then took the square root of the side because the hydroxide was squared. You got that the necessary amount of hydroxide to begin precipitation of magnesium hydroxide is 1.9 times 10 to the negative 5th. For the copper, we set up the same thing, except for this time copper was 0.02, hydroxide was squared, divide both sides by 0.02 and square rooted it, just like you did up above, and you got the hydroxide ion concentration necessary to begin precipitation of copper hydroxide to be 1 times 10 to the negative 9th. So taking a look at these two numbers, all you have to ask yourself is, which one's smaller? Because that's the one that'll start the precipitation the soonest. And you can see right here, it's the copper hydroxide that would precipitate first, and secondly, the magnesium hydroxide would precipitate second. Good luck with your precipitation calculations.